Okay, in this presentation we are going to look at bivariate random variables, bivariate probability distributions. So we have two continuous random variables, x1 and x2, that jointly have a bivariate normal distribution with an expectation of minus 1, 1 transpose. Essentially, that's just a matrix notation, but essentially what we're reading there is that the mean value mu of x1 is minus 1, and for x2 it is 1, okay? And we have a covariance matrix here, 1, 2, 2, 16. Okay, so this is a crucial part of this question, really, is the covariance matrix. Okay, so A, find the correlation between x1 and x2. Let y1 equal sum of x1 and x2, x1 plus x2. Write down the expected value of y1 and the variance of y1. Let y2 equal kx1 plus x2, where k is a constant. Find the value of k such that y2 is independent of y1. Okay, so a lot of work is going to be done here using the covariance matrix. Okay, but let's just remind ourselves what the formula is for the correlation. So correlation rho between x1 and x2 is given as follows. The covariance of x1 x2 divided by the square root of x1 times the variance of x1 times the variance of x2. Okay, so the square root of variance of x1 times the variance of x2. Okay, just in case I fluffed my lines there. So we're looking at the covariance matrix here now. So typically the notation is sigma, and it's a 2 by 2 matrix for two variables. So in the top left-hand corner, we have the variance of x1. Okay, that's 1. In the bottom right-hand corner, we have the variance of x2, which is 16. And in the top left corner and bottom right corner, the top right corner and the bottom left corner, I should say, we have the covariance. Now, that's a symmetric matrix, so those two values should be the same. Okay, so in both cases, we have 2. Okay, so covariance of x1 and x2 is 2. So using our values there and using the correlation coefficient formula up above, we have rho equals 2 divided by the square root of 1 times 16, which is 2 divided by the square root of 16, which is 2 divided by 4, which is 0.5. So that's the answer to the first one there. Straightforward enough. Okay. Moving on. The expectation and variance of y1. So let y1 be equal to x1 plus x2. So essentially the expectation of y1, e of y1, is simply the expectation of x1 plus x2. And essentially you just add them together. Okay. Just at the start, we were told that the expectation of x1 was minus 1 and the expectation of x2 was 1. Add them together. Minus 1 plus 1 is 0. Okay. Now the variance is a bit more work here. Okay. So when we're adding two variables and we want to get the variance of the addition of those two variables, we use this formula here. The variance of y1 is equal to the variance of x1 plus x2. Okay. Now this is the important bit here. The variance that is equal to the variance of x1 plus the variance of x2 on their own, plus 2 times the covariance of x1, x2. Okay, now that plus 2 times the covariance, that's because we're adding the variables. Okay, x1 plus x2. Okay, so if it was, so anyway, the 2 times covariance of x1, x2. So substituting our values in, we have variance of x1 is 1, variance of x2 is 16, plus 2 times the covariance is 2. So we 1 plus 16 plus 4, that is 21. So the variance of y1 is 21. Okay. Now, we want the look at y2. Okay, let y2 equal to kx1 plus kx2. So for y2 to be independent of y1, the covariance must be 0. So the covariance of y1 and y2 must be 0. Okay? Now, what is the covariance of y1 and y2? Well, that is equal to the covariance of x1 plus x2, which is how we define y1, plus k times x1 plus x2, which is how we define y2. So essentially what we have to do is expand that expression there. Okay, so that is equal to essentially the first term and each y1, essentially we get the covariance of that with each term in the second, each component of the second term. So we have the covariance of x1, kx1, okay, and then the covariance of x1, x2, okay, which is the second component of the second term, okay, and we're done then. So now we go to the second term of the first component, or the second component of the first term, I should say, which is x2, and do the same thing. So we get the covariance of x2, kx1, plus the covariance of x2, x2, okay. So essentially, each combination of a value in a component of each component of the first term with every component of the second term, basically, is what we have to do here. So the covariance of x1 and kx1, that's just k times the variance of x1, okay. Covariance in x1 and x2 is something we know already. The covariance of x2 and kx1 is simply k times the covariance of x2, x1, okay. And the covariance of x2, x2 is the variance of x2, okay. So essentially the key thing there really is just knowing that if you have a constant term for the covariance, you can just bring it out, okay. Specifically for the covariance, if you just have a scalar term, you just bring the multiply it, filter it out of the equation of your term. So that's it really. So anyway, that becomes k times 1 plus 2 plus k times 2 plus 16. That works out to be 3k plus 18. Okay, so for y1 and y2 to be independent, the covariance must equal to 0. Okay, so essentially we need a value for k that makes 3k plus 18 equal to 0. Well, necessarily that is minus 6. So this value of k that makes y2 independent of y1 is minus 6. Okay, so that's it. Yeah, we'll leave it there.